This video is for Physics AP. It's the kind of extra chapter that we would do that just brings together a whole bunch of little tiny topics that we've either not discussed at all or only barely discussed. You're going to notice it kind of bounces around a little bit. You will need at some point to go and print yourself off this note template. I'll have that resource online, and I'll have the filled in one too if as a last resort that's what you need. This particular document has a lot of color in it, and much of this chapter talks about different colors of things. And so you can see we're going to be kind of looking at rainbows and just different things that have quite a bit of color in them. So if you can print this note template in color, that would be really, really useful for you. And I'll see whether there's a possibility of getting that done at the school, but that's actually fairly unlikely. So just be aware of that. All right, here we go. A whole bunch of little miscellaneous little topics. We're going to start off with some quantum mechanics stuff, and we're going to look at the wave-particle duality of light. A lot of just raw content in this this whole note template. Once we have that raw content, then we can start doing some critical thinking. So some thoughts here. It turns out that light can be both a particle and a wave. I'm going to say or a wave. It'll always be one or the other, kind of depending on the experiment that you're doing. So I'll put in a little note here, just depending on the experiment. So you might be doing one experiment where you notice that, oh, it's behaving like a particle. But then you can do another experiment and go, oh, well, it seems to now be behaving like a wave. So some evidence for light actually behaving like a wave. You know, what are some of the experiments you can do where you can say, whoa, that only happens for waves? Probably the classic one would be, and we've done this earlier, in fact, very early in the course, that two-slit interference pattern. It was our second unit. When you have light going through a couple of slits and you get that pattern of interference, it only does that for waves. Evidence for particles, one of the things we're going to talk about here, because we haven't really mentioned it enough, is going to be something called the photoelectric effect. And that'll be actually kind of about a third or so, maybe even a little more, well, about a third of the pages in this booklet. Some foreshadowing, just to let you know what's coming up. Not only can light be both a particle or a wave, depending on the experiment, but things that have mass. So I'm just going to put in here masses. Okay, let's keep them small, though. Let's say things like, oh, electrons. Okay, so definitely not light, but things like electrons that are massive, well, you know they can be particles. We've always talked about them that way, but they can also be waves or particles. So we've already seen that they can be those particles. The key thing here is like, whoa, they can actually be waves too, which is pretty interesting. Okay, again, a lot of just raw content here in this note booklet. Light being a wave, well, if it's a wave, then it's going to have wavelengths and frequencies. So if you've got your classic little experiment where white light, which actually has all of the different colors in it, go and strike a prism, we're going to see it actually spread out into a whole bunch of different colors. The fact that it spreads out happens because a lot of objects like glass don't have exactly one index of refraction for each color, so for every color. So this is called dispersion. I guess because it disperses the colors into different angles. So dispersion is the issue where each color has a slightly different N. That was that index of refraction. Okay, so for looking at the rainbow, these are the colors that we get to see with our human eyes. There are other colors out there, but we just don't get to see them. Red is going to be the range of your visible light that you can see that has the longest wavelengths. We've got long wavelengths here. For red, I'm going to round to the nearest 100 just to make life easy. I'm going to say that, yeah, around 800 nanometers. Okay, and just a little note here. Okay, 1 nanometer is equal to 1 times 10 to the negative 9 meters. Okay, just as a conversion. And then on the blue end of your vision, well, it's the purplish end, I guess. I just like to call it the blue side. Okay, on the blue side of things, those are very short wavelengths. And I'm, again, rounding pretty liberally here, just to the nearest 100. But you're looking at around half the wavelength, at around 400 nanometers for blue light. Now, again, there are other lights out there that we just can't see. Once you go below red, then you start getting into radio waves. Okay, they're way down there. You go into the infrared and the far infrared and microwaves, radio waves. Okay, they're down there. And then X-rays are up here after you go past the ultraviolet. And after X-rays would be gamma rays. Well, you can always use that wave equation. We've used this a lot. And for light, when you're playing around with light, the speed of light gets its own letter of the alphabet, C. And seen this quite a few times, 3 times 10 to the 8 meters per second. So hey, we could go and use this to try to figure out some frequencies here if we wanted to. So for red light, just using the wave equation, V is equal to lambda F, we know that the speed has to be 3 times 10 to the 8. And the wavelength, we'll just call it a nice 800 nanometers, 810 to the negative 9, and let's go and look for the frequency. And when you do that, you'll find that the frequency is very fast, 3.75 times 10 to the 14 hertz. Okay, so I'm not going to ask you to memorize that, but just be ready to find that frequency. Might be useful to know that the wavelength for red light's around 800 nanometers could be helpful. Blue, again, I'm not going to ask you to memorize the frequency, but maybe the wavelength. But it would be, good critical thinking skills to be able to say, hey, without my calculator, I can already make a prediction on what this frequency is going to look like compared to red. It has a smaller number here, okay, only 400 times 10 to the negative 9, but it still has to reach that product of 3 times 10 to the 8. So to do that, the frequency needs to be bigger, okay, 7.5 times 10 to the 14 hertz. So for red light, the one that has the long, big wavelength, it's actually got a small frequency. But for blue light, that's actually got a large frequency. Really important to remember. Just which one's got a bigger and smaller frequency. Okay, great. That's if you want to say, oh yeah, light's a wave. Okay, well, next page. Let's change the rules. Light's also a particle. Okay, it's made up of these things called photons. Some things I can tell you about photons, they have no mass at all. So their mass is equal to 0 kilograms. None. Absolutely 0. But what's crazy, they do have momentum. Now you can't use your traditional P is equal to mv. It doesn't work because the mass is equal to 0. So there's a different equation that we use when we're talking about light, when we're talking about photons. And the equation for how much momentum a photon has, it's actually equal to a constant, which you've used before. We'll see it again here today, Planck's constant, divided by the wavelength. Now it turns out you can actually, using Planck's idea for how much energy there is in a photon, okay, we'll see these conversions soon, but you could also take the amount of energy that's in a photon and divide by the speed of light. That also works. So just a couple little notes. A lot of this is kind of foreshadowing for some stuff we'll do in a bit, but this is Planck's constant. This is just the amount of energy in a photon. And this C is the speed of light. And that'll let you figure out how much momentum there is. Okay, well, they are like little particles. And these photons, they can collide with things like electrons. They can have collisions. Okay, so we're going to have some stories about some collisions in there. Guess who your friend is? As always with collisions, it's momentum. Okay, momentum is conserved. So we can use that as a little problem-solving tool. We know that we'll have the same amount of momentum before as we do after. Okay, let's get back to this Planck's constant thing. Photons, we talked about this in Physics 11. Photons do have energy. So these little specks of light, as they're flying through the air, each one of those little specks of light has some energy. And the amount of energy each one has is Planck's constant, just a number, multiplied by the frequency for that particular color photon. So Planck's constant, something you just find on the formula sheet. Okay, so this was Max Planck's work. And to a couple of sig figs, it's around 6.6 times 10 to the negative 34 for our units that we use. Key thing, Planck's constant is a constant, but the frequency can change depending on the color. And blue photons have a higher frequency, so blue photons, bluey purple ones, they're going to have more energy. Okay, really important thing to keep in mind all the time. Okay, so blue photons have more energy than red. And green would be somewhere in the middle. So as you look at that rainbow, what you're going to find is as you move your way towards that bluey purple end, where yes, the wavelengths get smaller, the frequencies get bigger, so the energies increase. Okay, here's kind of a classic little question where once you know that light can be made up of these photons, and radio waves are kind of a form of light that we just can't see, you can do this radio station question. If you didn't know about the whole photon thing, you'd be going, what is going on? But here, we can actually do this now. It's not actually that hard. So it says calculate the number of photons per second from a 97.1 megahertz Sun FM transmitter that's operating at 1.8 kilowatts. So that's, I think, actually the value for how many watts that FM radio station actually broadcasts at. And so if you look at what's happening, can you draw a little picture here? I've got the ground, and somewhere in the valley, they've got a radio station antenna, and they're broadcasting radio waves. Yes, you can think about it as being radio waves. That's the way most people think of it. But another way to look at it is to say, oh, it's like these little photons are coming and flying off the antenna. Okay, and then hopefully they hit your radio in your car, and then you can actually hear the radio station. But they're flying out of there, right, actually at the speed of light in every direction. And we can figure out how many actually come out every second. Now, there's a few different ways to do this, a few different ways to start this. I'll just show you one option here. They did mention that the power of the radio station was 1.8 kilowatts. Okay, great. Just converting that just to watts, that's 1,800 watts. Better way to think about it though, even though we'll write watts and say watts, that's 1,800 joules of energy every second coming out of that radio station. All right, what else do we know? The frequency. Yeah, okay, I know on my radio station dial it's just 97.1, right? Megahertz. Well, mega means millions. So the frequency for that radio station is 97.1 times 10 to the 6 hertz. And now I've got it in my usual physics units. Okay. Again, a couple of different ways that you can dive into this problem. Here's one option. I'm going to kind of split my thoughts here at the beginning. Let's find out the amount of energy in each photon. So every single photon coming out of the radio station, it's going to have some energy based on this relationship from Planck. E is equal to hf. So I'm just going to go and figure out how much energy they've each got. It's not very much. So I'll take Planck's constant. It's like 6.626, 10 to the negative 34. Just look that number up. And then the frequency here, 97.1 times 10 to the 6. So it's a color you can't see. When you stare at that transmitting radio station antenna, you don't see the light coming off. What it is, it's just coming off in the form of radio waves. And the amount of energy in every one of those little photons, 6.43 times 10 to the, get this, super tiny here, negative 26 joules of energy in every one of those photons. Not very much. So an amazingly small amount of energy in every one of those photons. But somehow we're actually getting 1,800 joules coming out every second, so we can go and figure out the number of photons per second. We need a lot in order to get up to 1,800 joules. There's not very many on each one. Just thinking about the way the units are going to cancel out here, we can just do a little division. We can say, okay, look, we need to get to 1,800 joules in every second. Right, this is kind of a per second story. And if we divide that by how many are on board each one, we divide by 6.43 times 10 to the negative 26 joules of energy on board each photon. Well, you can see the word joules cancels out, and then you've got like a double divide going on, so we're actually going to end up with photons when we're done. And it is a lot. 2.8 times 10 to the 28 photons coming off this radio station antenna every second. Just out of curiosity, I kind of swung that over to chemistry just to take a look. Just random trivia. It's like 46,000 moles of photons coming off every second. All right, moving along here. The next thing we're going to work on for a couple of days, for this lesson, finishing it off, and then for a couple more, is something called the photoelectric effect. We did talk about this really briefly in Physics 11. The whole idea here is that as long as you've got photons with enough energy, so how about I say high energy? If we take some high energy photons, okay, like, you know, think blue, right? Like up in that blue end of the spectrum. If we shine them at some metal, high energy photons, like blue photons, they can possibly, for the lack of a better verb, they can kick electrons free from the metal. Okay, so here's the plan. I've got like a little slab of metal here with some electrons on there, and then here comes some incoming radiation. So this, on the left side of your screen here, this is some light coming in, made up of photons, right? So some individual little photons are coming in here, inbound, and they're going to strike that metal. And as they come in, each one of those photons has some energy on board. It's only going to work if their color is blue enough, right? They have to be near the blue end of the spectrum. Okay, so let's put a little note. This only works if the frequency, F, is large. Probably won't work with red light. Might work with green, will work really well with blue or with purple. We might actually have so much energy coming in those individual little photons, there might even be some leftover energy. So one of the parts of the photoelectric effect equation is the leftover energy part. And so if there is some leftover energy, and by leftover I mean after it's paid the price to kick the electron free, that leftover photon energy is converted, it's kind of donated into kinetic energy for the electron. So here goes an electron flying out of there. They're leaving, with some speed, right? They've got some velocity because they may have been kicked so hard by those incoming photons that there's actually enough left over to give those electrons a little bit of speed. So here are some speeding away, some speeding electrons. And yeah, they've got some kinetic energy, each one of them. Some 1/2 electron mass times speed squared. That's the plan. Okay, let's just take a little closer look here. Got this slab of metal, right, with some electrons in there, kind of waiting to be kicked out. So this big brick here, this is the metal. Some metals actually give their electrons up a little bit easier than others, and some are a little tougher to actually give them up. And so each metal type, sodium or aluminum, each one has a very specific value of energy necessary to knock them free. And we're going to call that the work function. People use different symbols. Let's use the symbol phi for that. That's going to represent the energy needed. And this is metal specific. This is the energy needed. So I want you to be thinking like joules. This whole equation I'm going to show you here in a second is just nothing but conservation of energy. So it's got everything kind of written in joules. So that phi is going to represent the energy needed, measured in joules, to free an electron. Let's give it a name. We'll say that is called the work function. You have to work that electron free, and each metal has its own value, so it's a function of the metal choice. That's kind of where it gets the name work function. Now, a little higher level thinking issue that we won't get too far into today, but in the next lessons we will. If you're going to try to knock electrons free that are found a little bit deeper than on the surface layer, be aware of the fact that they're harder to knock free. So a little thought here. Electrons deep in the metal they have a higher work function, a bigger work function. Okay, so the equations. What do we need to know to actually get this thing called the photoelectric effect to work? I'm going to split my page actually into 3 here. I'm going to put the main equation in the center and then some little subsidiary equations over on the side. Here's the main equation. It says that when that photon comes in, it's going to have some energy based on its frequency. So that's all about the photon on the way in. I'm going to switch colors. A lot of people wrestle with this equation because they don't appreciate the fact that it actually talks about 2 totally different things. So HF is the amount of energy on the way in for that photon that's going to no longer exist. It gives up its existence to do this. It strikes that metal and hopefully can work an electron free and maybe even have a little bit left over to give that electron some kinetic energy. So think of it as like an in and an out. you've got this much energy coming in available to you from the photon, and then where are you going to put it? Where's it going to go? Well, here's where the out of that energy is going to go. So on the left side here, let's talk about these photons. They give up their existence. They sacrifice their existence to pull this trick off. If you're ever trying to figure out a frequency, you might have to use the wave equation. People might give you the value for the wavelength, and you might have to go, oh man, I got to find the frequency. Not a big deal. The speed is the speed of light, because on that side of the equation, you're dealing with photons that go the speed of light. And then the wavelength will have to be in meters, and then you'll end up with a frequency that's perfect. It'll be in hertz. Then on the outside, the heading outside of the equation, let's talk about the electrons that get knocked free. The kinetic energy will just be 1/2 the mass of an electron and then its speed squared. It goes away at much less than the speed of light. And the mass in this part of the equation would be just the mass of an electron, something you'd go and look up. 9.11 times 10 to the negative 31 kilograms. Okay, one more page for today, and then this lesson is done. Let's take a look at the setup. And I have stolen this little screenshot here from the little online PhET applet, and you should definitely try this out. So if you type in PhET, which they spell as PhET, it's an online resource that lets you do these little simulations. Okay, so if you want to do a little Google search for PhET and then photoelectric effect, you'll find this. It'll end up looking something like this. Okay, so here's the little application ready to run, and I'll turn it on here in a minute and you can see how it looks. But that's the little online deal that's free, and you can try it out. And the light bulb, the little desk lamp up there, has a couple of words associated with it. One of them is intensity. So this is just going to be the amount of light, not the color, but the amount. So it's like the light bulb is on a dimmer switch. Think of that as controlling the number of photons per second. The frequency, I can adjust that actually by adjusting the wavelength in this story here. The frequency, that would be the letter F. Okay, that would be measured in hertz. That affects the color. Which is another way of saying the wavelength and energy per photon. So for my sliding controls here, I can pick the color. Right now in my notes here it says 510 nanometers, green. I can slide that around and make it blue or purple, or I can go red, and then intensity is like a dimmer for how bright that light would actually be. And so the plan is that when this light bulb is running, I have to turn it on, and I'll show you that in a second here. When I turn the light bulb on, photons of the color I pick are going to come flying out of this light. They're really tiny, so you don't even see them, right? Like these little specks of light that come flying out. Too tiny to be seen in this animation. And they're going to go and strike this brown slab, which is supposed to be some metal. I don't know, maybe it's like copper or something like that. And on that brown slab, there are going to be some waiting electrons. They're like, oh yeah, I'd really like to go flying through the air here, but I don't have enough energy to get free from the metal that I'm stuck to. So if you look really close, there's some little blue electron marks there saying, oh yeah, there's some electrons that are waiting to go. And when I turn the light on, as long as the photons coming in have enough energy, they will kick these electrons free. And so these little blue spheres here, they're going to come flying out of there with some velocity. And those are going to be the freed electrons. The price has been paid by the photons in order to free them. And some of them are going to have more velocity than others, and you'll notice that if I use a battery to make an electric field, I can actually make them speed up once they're flying. So the battery has a negative end and a positive end, and you can actually switch around the orientation of the battery, but for now I'll run it the usual way, which is like this. And you can see on the right hand slab of metal some little plus signs because electrons are missing, and that's going to create an electric field. So if you think about electrostatics, when we're doing that in chapter 5 of Physics 12, there's this electric field in here that's warning people, saying, hey, watch out, if you put positive things in here, they're going to get shoved to the left. Well, we have no intention of putting positive things in there. We're going to put electrons in there. So they're backwards. They disobey electric field warnings, and they're going to get accelerated to the right because of that voltage creating some negatives on the left terminal and positives on the right terminal. Also in the setup is this ammeter. Okay, the job of the ammeter is to just record the current. It's going to record whether or not we're successful getting this experiment to run. So if we can free up some electrons, then they'll go and work their way through the circuit. The ammeter will show that it's happening. So you can think of this as recording. I know that the units are not exactly right, so I'll use air quotes here. It's recording the number, air quotes, not exactly, because it's recording amps, but the idea is it's giving you a feeling for the number of electrons per second. So a purist would say, whoa, that's not right. It's not electrons per second, it's coulombs per second. Yeah, I know, I get it. But it's generally telling you whether or not we've got some current flowing. Okay, last two things for today, and then I'll just kind of show you this thing running. The battery, when it's positioned there, it turns out it will not pull electrons off the metal. It just doesn't have enough electric field to do that. But it will speed them up. If you can knock them free with photons, and they're in that little space, then that battery will create a force in there, and it will make them gain speed. Because it will not pull the electrons off of the metal, the battery by itself will not cause more electrons per second. And by that I mean being knocked off the metal. But I will say this. If you wire it backwards, this is down the road a couple of days, but it can cause less. So this is an issue for down the road. Don't worry about it too much today, but to make the notes complete, we will look at something called stopping potential, stopping voltage, where the battery can actually shove the electrons backwards. It's like, go back, right? But it can't actually pull more off. Okay, so I'm going to fire this machine up just so you can see the actual little online free app. You should try this out. Okay, you should on your computer at home, you should try going to the PHET site, P-H-E-T, and then photoelectric effect, where you can then online, just in a browser, you can run this. And so I've got mine set to a green light, and I'm going to turn my battery up. I'll make it similar to what you see on the notes here. Let's go for 2 volts. So I'm going to dial this up to 2. Get pretty close there. Okay, so I'm at 2 volts. I don't have any current flowing, even though if you look closely here, there are some little electrons there. They're like, oh yeah, we don't want to be here. We'd love to fly through the air, but nothing is knocking them free. So now I'm going to turn the light on. And when I do, I've got green light. That should be strong enough. When I turn this green light on, then it starts knocking the electrons free. And once they're free, then the battery's actually going to make them go even faster. So they come out of there with a little bit of velocity, and then they actually pick up speed because of the battery, and they make their way over to the other plate. And I can see on my little ammeter here that I am recording some current. So it's like, yep, that is successful. You do actually have some current flowing. Now remember the issue with colors. Red, although it has a bigger wavelength, has a smaller frequency, so it's got less energy per photon. So I'm going to turn this into a red light by just putting the slider over here. So there are red photons that are striking this metal right now, but each one of them does not have enough energy to knock an electron free. Even if I turn the light intensity up to 100% and make it a really bright red light, each one of those little particles as it comes in never has enough energy to knock an electron free. And the math, the statistics of it says you'll never have an electron get struck by two photons at the same time. It just doesn't happen. So each time an electron gets hit by a photon, it never has enough energy to wiggle free. And what energy it does get, it just kind of turns into heat. So each strike by a red photon just isn't good enough. But if I even turn my light down, I don't have to have it very bright. I'm going to make it 20% or so, but I'll make it a bluey purple light. So I don't have a lot of photons coming off the light every second, but each one of those photons, I can't even see them here. They're so small. When they strike that plate, they're actually causing the electrons to get knocked free. And I can see that showing up as a current. And if I go to blue, blues are good enough as well. Still getting some photons coming off. And if I go to green, yep, okay, if I'm careful with my choice of green, then I will get some photons coming off. But if I go up into the yellows, then up in here, nope, no photons at all. And each metal is a little bit different for what color will work. It's called the cutoff frequency. So this is sodium, and I can switch it over and try like copper. And I might find that copper is even harder. Actually, it does look like it's harder. Got to get up into the violets, maybe even into the ultraviolet in order to get copper to work. Actually, yeah, way into the ultraviolet. Can't even see that light in order to get that to work. And then different metals. I don't know, maybe zinc is easier. Maybe zinc is harder. Okay, so let's try zinc. Does zinc work with purple? Nope, not with purple. Into the ultraviolet. Deep into the ultraviolet, zinc seems to work. You can try any one you want. You can try calcium. So calcium works with maybe purplish. The sodium one seems to be the easiest one to get it to work. Okay, so each metal has its own work function. So with sodium, yeah, even a green will knock them free, but red will not. Red will not. So that's called the photoelectric effect. For this first day, you should just make sure you have access to that app and you can try it out, because on the next couple of days' notes, we're going to play around and make some changes and do some critical thinking now that we've got something to actually work with. So this marks the end of the first day of the extra units chapter.